here we go. We're going to start with number 1 and see where it takes us. All right, so a train on a straight track goes in the positive direction for 5.9 kilometers, then backs up for 3.8 kilometers. And my guess is from that they're going to ask us a lot about distance and displacement. So here on my handy dandy sheet, why is this thing difficult? Oh, and I uploaded PDF copies of this sheet to the general folder. So if you want to use these for your homework, you're more than welcome to. You can just print out your own. No, these are the problems online that you went and looked at and did your Y's for. Okay, we're done with that packet. I may come up again in review, but we're basically been there, done that. So I would definitely show that I understand displacement is how far I am from where I started including direction. And maybe switch colors. And then I know the distance is the length of my path. Now, there's hundreds of ways to say that. That's just how I'm choosing it. But what you really want to focus in on, can you hang that on the wall? It's just easier for people to see. Thanks. Is that you showing the person looking at this that you really understand the difference between distance and displacement, right? Because that's what this whole problem's about. I might actually, in this problem, include a diagram also, just to show them. So positive direction. Which way do you guys want to say is the positive direction? This way, to the right. Okay, let's do that. So I'm going to say my train starts here, goes here, turns around and comes back. And let's see, 5.9 kilometers. And 3.8 kilometers. And like yesterday in the example problems, I'm going to draw in that displacement vector, right? So this is very, very similar to that example problem we did with going to the store and everything like that. Yes? No? Maybe? Yeah. So let's see what they want to know. Is the distance covered by the train greater than, less than, or equal to its displacement? I'm going to let you answer that one because I don't want to answer the multiple choice for you. What is the distance covered by the train? Now, let's see, everyone has different numbers. So my distance, if I remember from yesterday, is how long my path is. So that'd be 5.9 kilometers plus 3.8 kilometers. I'm having like deja vu. And that would be for me 9.7 kilometers. So I should try that, see if it comes up right. Let's see. Give me my keyboard. 9.7. Oh, I must have left. I usually turn that off, and I must have forgotten to turn it off for this problem. Yay! I got that one right. What's the train's displacement? So, my displacement is, if I look at my equation sheet, remember this is my equation here for displacement. Delta D equals D final minus D initial. So, probably, I'm just going to go through because I want to put this. All right. So I'm going to call this point 0. And what I'm looking for is where I am at the end of that. So that's going to end up being I'm going to end up, I don't go beyond where I am, so I'm going to end up 5.9 kilometers minus 3.8 kilometers, because that'll give me that green segment, which ends up being, what, 2.1 kilometers? Now, it's really bad. I did not use the actual equation. But I know the answer is correct because I can visually, from my picture, see where I am. So let's see if it's correct. I bet it is. I forgot to turn off the units. Yay! And I think that's it, right? Good. All right, so number 4. Expected father paces back and forth producing the position versus time graph shown in the figure. Okay, so we got this position time graph here. Calculate the father's velocity for segment A. Calculate the father's velocity of segment B. Oh, we got to do units. Segment C and segment D. So it's all focusing on getting velocity from this position time graph. So that's what my Y should focus on. Showing that I understand what's the connection between a position time graph and velocity. And so new page. Good. So number 4 here. And I'm going to start off by showing that I know that velocity is the rate position changes. The velocity is the rate position changes. That's just kind of the definition of it. How's the rate of change connected to a graph? Well, the slope of a position time graph is the velocity. We did that a few weeks ago. Right? We did a whole interactive about carts moving. So we need to find so now for doing the Y part of it, the Y part's done, we do the how part. We need to find the slope for part A, part B, and part C. I think our equation sheet has slope on it. Let's see. Nope, I guess it's so general that I expect you to know it. But we could use the physics equation instead, and we'd use that velocity is delta D over delta T. That would be our equation for the how. So which in terms of slope is rise over run. Right? Because D is on the y-axis and X is time. So for part A, What's our rise? What's our change in position? Anybody? 2. And what's our run in time there? 1. Right? So we'd have delta D is 2 meters over 1 second. That'd be 2 meters per second. B, you do the same way. C, you do the same way. What do you think about D? Do the same way. Yeah. Now, the only kind of caveats here, what do you notice about B? There's no slope, so what number is it going to be? 0. What about D? Look at D. It's going to be negative, because you're going to have a negative rise over your run. All right? So B is going to be 0. C will be some positive number. D will be a negative number. But you do them the exact same way. Delta D over delta T. Rise over run. And you get the slope, which is the velocity. Questions on this one before we move on? A severe storm on January 10th, 1992 near the Aleutian Islands caused a cargo ship to spill 29,000 rubber ducks into the Basque-Coast into the ocean. I just thought this was a cute problem. 10 months later, hundreds of rubber ducks began to appear on the shoreline near Sitka, Alaska, roughly 26,000 kilometers, 2,600 kilometers away. What is the approximate average speed in meters per second of the ocean current that carried the ducks to shore? All right. Express your answers. So this is about that. Let's see. This is number 3. If they're asking for the average speed, why don't we just assume that they always moved at that speed, right? Because if you move at an average speed of 60 miles an hour for an hour, how far do you go? 60 miles. So let's assume move at average speed. So it will take longer time if they are slower and less time if faster. So I'm just trying to show that I understand kind of the situation, okay? And I could, I could define speed or talk about what distance is. Although I might put in there speed is related to distance. So then now I'm moving over to my how, and I'm going to go and look and see, okay, is there an equation in my section that talks about, traveling somewhere? And I have this D equals D naught plus V initial plus V delta T. So that's the equation I'm going to use. Now, D means how far I travel, or where I end up, depending upon how you're using it. D naught means where I start. What do you want to call where they started? How about 0? It's an easy number. We call it 10. I'd rather call it 0, though. So, how far away did they end up? That's a character called a naught. Do I know how fast they moved? No, that's what they're asking me to find. Do I know how long it took? 10 months later. So that means, let's see, if I isolate B, I get 2,600 kilometers over 10 months equals V. So that means V equals 260 kilometers per month. It is. It's a rate that your distance is changing, right? What units do they want me to use? I know. What does it say? Meters per second. All right. So kilometers per month is kind of a wacky unit, isn't it? I would rather get rid of all my units beforehand so I don't have to worry about them and then do my math. So maybe we should do some units here. If I want to take 2,600 kilometers, how many meters is that? Well, is a kilometer bigger or smaller than a meter? Bigger. So I'm going to get a bigger value, right? And there's how many kilometers in a meter? 1,000, right? So what I'm going to do is I'm going to take this number. What number can I multiply by, any number by, and not change the amount? The number 1, right? Because what's 5 times 1? What's 23,497 times 1? So whenever I do conversions, the way I think about it is multiplying by the number 1. So I'm going to put kilometers on the bottom because I want to get rid of them, meters on the top. And there's 1,000 meters in 1 kilometer. And that's just a fancy way of writing the number 1, right? Same over same. So I'm going to end up with 2, 6, 5 meters. I did the math in my head. Now I've got to get 10 months into seconds. So, does anyone know how many seconds in a month? No, okay. What do we know about months? Days. How many days in a month? 30. So let's put months down the bottom, days up top, 30 over 1. Now we're going to be in days. Do we want to be in days? No. What do we know that are in days? Hours. Okay. So we do hours up top, days down the bottom, 24 to 1. Now we're in hours. Do we want to be in hours? We want to be in minutes. Okay, minutes, hours, 60 minutes in 1 hour. We don't want to be in minutes, though. We want to be in seconds. So minutes down the bottom, 60 seconds in 1 minute. I need my calculator. Oh, you know the other way we could do it? Oh. I bet if I went up here and I went out to good old Google And I put in like 10 months to seconds. I get the answer. Hey, 2.628 times 10 to the 7th. Well, no, that's how many, that's my time. So, what was that? 2.628. 3 times 10 to the 7th seconds. That's like 2, 6, 3, 1, 2, 3, 4, 5 seconds. Now I just do my same equation. 2,600,000 meters equals V times 2, 6, 3, 5 seconds. A lot of zeros. Let's hope some of them cancel. That would be nice. 2, 6, 1, 2, 4, 5 meters over 2, 6, 3, 2, 3, 4, 5 seconds. And those two cancel, those cancel, those cancel, those cancel, those cancel. I'm left with 26 over 263. Will, what did that come out to be? 0.098. 8 meters per second. I hope that's right. That was a lot of zeros.